Okay, if you could all just give me 1 sec, I'm trying to get the hybrid technology situation set up, and then we can get started. Um, I will drop the link to the GitHub that has the materials in the chat. You can also find these on the CSDE website now. Sure. Okay, question for those of you online. Can you hear me? All right.
Yeah.
Okay, we're having some trouble with the in-room desktop that I would also log into to do like really good audio. But if y'all can hear me on my laptop, I'm just gonna use my laptop then, and I'll push that to the projector for those who are in person. Okay, so let me pull up my slides and then we can get started. Great. Okay. Hi, everyone. My name is Jessica Godwin, for those of you who don't know me, and I am a statistical demographer here at the Center for Studies in Demography and Ecology at UW, and I'm also the training director for a graduate certificate program here. Just heads up, this is only the second time I've taught these two workshops with an eye on extending this series into something with MCMC and Gibbs sampling, and then also something with STAN and NLaw. But this kind of arose out of many of our students' need to kind of get the very background and basics of Bayesian statistics and probability and the math behind it. So we're not going to fit any models today. We're not even going to look at data. This is just kind of helping you understand what we mean when we say prior, posterior, and likelihood, and how we write those things down, and how we can calculate posteriors in an analytical way. So thanks for your patience also with me having to reschedule last week. The workshop that was supposed to be today on inference will now be on Monday. So if you didn't get that update, let me know at the end of class and I'll be sure to send you an email. All right, let's get started. So please also, in Zoom, I can't really see you, or I might not be paying attention to get your to see your hands raised. So please just, interrupt if you have a question. I don't want you to wait long. So let me for our in-person people. There you go. All right. So we're gonna start off with really just some basic probability. But I do want chat. Yes, the slides, sorry for those of you who maybe just came in, the slides are oh, I sent them to the waiting room participants, not to everyone. That's okay. Here's where the slides are, as well as the underlying R markdown file, if you want. Okay, hopefully that's the last person coming in. So here, just for those of you who may want to, do more research later or whatever it is, these are kind of the books I use to create this set of notes. Bayesian data analysis, the 3rd edition, the Gelman book is really good, but it's definitely more statistical. So I think having a good understanding of statistical theory would be important if you wanted to kind of to use that book. So I wouldn't just dive in. What is my R yelling about? No, I don't want to do that. Okay, so then Statistical Rethinking is kind of a cool book if you are someone who wants to use Bayesian models in your research, but maybe you aren't coming to your research from a statistics or math background. And then Casella and Berger is kind of the bread and butter statistics master's theory level textbook. And so if you want to read more about conjugacy or Bayesian statistics in a really simplified but mathematical way, that's where I would send you. So the probability basics that we're going to need include some notation, and we're going to kind of build up to the classic Bayes theorem example, and then we'll move on to Bayesian statistics. So to start with probability, we always have to start with set notation. And so mathematically, a set is a collection of elements from a population, and we denote it with curly braces. So here we have a set A. That's just the positive integers less than or equal to 5. We have the primary colors in another set. We have the odd positive integers. Next. So a set can really be anything, but it's usually denoted with curly braces. We have a mathematical convention called the empty set, which allows us to define a set that has nothing inside of it. So for example, if I want the set of all integers greater than 4 and less than 1, that doesn't exist, right? There's no numbers that fit that criteria. So we would put this kind of 0 or circle with a slash through it to denote that this is a set, but it is in fact empty. On the other end of the spectrum, we have a set called the universal set. And if we're concerned with a population, this universal set, often denoted by capital omega, would represent all of the elements in the population. So here that, set A at the top of the slide, the positive integers less than or equal to 5 could be a subset of a universal set where the universal set was all of the positive integers. If we have two different sets, A and B, we need to think about notation for the intersection of those sets. So that's that little, what we call a cap in math, but the little kind of upside down U. You can think of it as translating to the English word and so the intersection is all the elements in A that are also in B, or in both of them rather. The union, on the other hand, you can kind of think of loosely as the English word or. And that is we have kind of the U shape, and that's all of the elements in either A or B. So for a quick example, if we have this set A that's numbers 1, 2, 3, 4, 5, and B, which is all the even integers 2 to 10, then the intersection A intersect B, we might read after the right arrow, we'd say A intersect B equals the set that contains the elements 2 and 4, right? Whereas the union of these would be all those first 5 numbers, 1, 2, 3, 4, 5, plus 6, 8, and 10. So you'll notice that 2 and 4 are not repeated when we list out the elements of A union B. If we have the set of odd numbers and the set of even numbers now, the intersection of these would be the empty set, and the union would be all of the integers. Or maybe we can argue about 0 if anyone really wants to. Okay. So all of that is necessary when we talk about probability so that we can properly talk about sample spaces, experiments, and outcomes. So in statistics or in probability, an experiment is an action or a process of observation. And once we perform the experiment only has one outcome. But prior to performing the experiment, there is usually a whole set of possible outcomes called the sample space. So, for example, if our experiment were to roll a dice, the sample space would be all of the possible results, the numbers 1 through 6. But the outcome would be just one of those things after we've rolled it. All right. So S we can kind of think of in the same way as that omega or universal set. And in fact, once you start to translate this probability notation into statistical spaces and to think about probabilities of parameters within support spaces, often we use these kind of notation interchangeably, actually, between S and omega. So an event, so we've talked about an experiment, that's a process of observation. We know that the sample space before we carry out the experiment is all the possible outcomes of that experiment, each outcome being a single element of the sample space. An event now is some subset of the sample space or a set and collection of one or more outcomes. So if we think about flipping a coin 3 times, I've listed out the sample space for us here. We could see 3 heads in a row. We could see 2 heads and then a tail, so on and so forth. There's 8 possible outcomes here. The event we might think about, say, is getting 2 heads. That's a subset of S, and it contains 3 possible outcomes, right? So this distinction between events and outcomes is important. Events are made up of outcomes. They can be a singular outcome, but they're often made up of one or more outcomes from the sample space. If we are interested in getting, an odd number of tails, we could list out that event as well, or any sort of event that you could make up about flipping 3 coins. So if we want to flip 1 coin and then roll a die, the sample space would look something like, we could get any of the numbers 1 through 6, and we could either get a heads or we could get a tails. And then we might say, we want to know if we roll a die, a value higher than a 4, right? So that would include getting a 5 or a 6, and either heads or tails. But maybe we're concerned with an event about getting a heads, right? So these are all just simple examples to distinguish this concept of events and outcomes, and make sure it's clear to you that events often contain more than one outcome. When we have a sample space that has a finite number of possible outcomes, calculating probability is really easy and intuitive, and most of us know how to do it without being taught. So if I wanted to make a visual representation of the sample space that represents rolling of a fair die, I might start with, this is really the underlying idea of a Venn diagram, that the area of the rectangle that you're putting circles inside of is equal to 1, and then the relative area of the circles or whatever you're drawing within the Venn diagram, which is usually representing omega or this universal set, is some comment or is a measure of the probability of getting someone from that group or some object from that group or an outcome. So here we have, kind of a visual representation of the sample space of rolling a die, where we could either get the numbers 1, 2, 3, 4, 5, or 6, all with equal probability, right? Those rectangles are of the same shape. So if I want to calculate the probability of the event, which is rolling something less than or equal to 4, I can either ignore the picture and count up the size of the event set and divide it by the size of the sample space. And when we talk about the size of sets, we're talking about the number of elements within them. So you probably didn't need me to tell you this, but the probability of rolling a number less than or equal to 4 when we roll 1 die is going to be 4 over 6, because the size of set A or the event A is 4, and the size of S, the sample space, is 6. If you want to think about a visual representation of this, you would think about the relative area of squares 1, 2, 3, and 4 to the whole area of the rectangle S, right? If I want to think about an odd roll, The size of that event B would be 3. I would get the probability of that event as 1/2. That's 3/6, right? The relative sizes of the events compared to the sample space, right? So if we want to think about unions and mutually exclusive events, which we already introduced this set notation for, but how this translates into calculating probabilities, this visual representation is going to come in handy quite a bit. So we have the same sample space. We're rolling a fair die as our experiment. We have 6 possible outcomes. We already talked about this event rolling less than or equal to 4, event A, on the last page. And now we have event B, which is rolling greater than or equal to 5. And then visually on this sample, this diagram on the right, event A is represented by the color blue, right? All of the outcomes that fall into that category are in the color blue. And event B is in red. Now, if we want to take the probability of A or B happening, it's really easy in this case because there's no squares on the right-hand side that are both blue and red, right? That is what it means for 2 events to be mutually exclusive. They do not have any elements in common, or rather, we would say their intersection is empty, is another way of thinking about that. So when we have events that are mutually exclusive like this, that don't have any events in common or any outcomes in common with their between both events, we can simply add their individual probabilities to get the probability of the union. So this becomes really easy. I would add the probability of event A, or the blue squares, which is going to be 4/6, plus the probability of the event B, or the red squares, which is 2/6. Or, as you can see visually, every square in my sample size is colored by event A or blue, or event B or red. And so the probability of either event A or event B happening is just 1, right? So if the union, if the 2 events that we want to calculate the probability of their union are not mutually exclusive, meaning they have elements in common or outcomes in common, we have to use a different formula that subtracts out their intersection. So here, we have, we're back to kind of that first example where we have the event A that we're going to roll a number less than or equal to 4. And then we also have event B, which is odd numbers. And if we added together just P of A plus P of B, it should be pretty easy to see that both of those events contain the outcomes of getting a 1 or a 3, right? Or those purple squares are going to be added. If I add up in the numerator the 4 blue squares plus the 3 red squares and divide by 6, obviously a probability can't be 7/6. As you can see here that if we just add P of A plus P of B, we're going to add that intersection twice. We're going to have added event or the outcome of getting a 1 or a 3 in both cases. So we want to subtract that out 1 time. So we would actually add 4, 6 plus 3, 6, and then subtract out that intersection of 2, 6. Any questions here? Person or online? All right. Okay, so another background piece of information that may be reviewed for some of you that we need to talk about Bayesian statistics is the notion of conditional probability. If we have 2 events, A given B, we can always write the probability of event A happening, given that we know B already happened, as the probability of their intersection over the probability of event B happening. So whenever you see this vertical line in probability notation, you want to read it as the English word given. So this is the probability of A given B, okay? If we multiply both sides of this equation by P of B, we also get another important relationship around conditional probabilities, that the probability of the intersection is the probability of this or the product of this conditional probability of A given B times P of B. So the way this works, suppose I went out in the hallway and were to roll a die, and then I yell back in, hey, it was less than 3. And then I ask you, what's the probability that the roll was odd? That is the experiment that we would be doing it to calculate this phrase right here. The probability of an odd roll given you know that the roll was less than 3. So before you know that it's less than 3, the probability of getting an odd roll, right, would be 3/6. Once I tell you it's less than 3, how many odd numbers are there less than 3? Well, that would just be this square, right? And so that would be only one opportunity or to get an odd number. And now there are only 2 options if we're less than 3. Okay, so we've kind of just restricted our sample space in a conditional probability from all 6 options to simply this red square. If we condition on knowing that the roll is less than 3, right? Then the only possible outcomes we have are 1 or 2. And the probability or event A in blue of getting an odd number only intersects with that restricted sample space at the number 1. So in this case, we can see visually that the probability that the roll is odd, given that it was less than 3, should be 1, this square, divided by 2, the size of the red. If we use our formula that we just learned, we can calculate the probability of odd conditioning on knowing that it's less than 3 or given it's less than 3 by calculating the probability of their intersection in the whole sample space. So that's just this purple square, 1/6, and dividing it by the probability of event B, which is the red square, which is 2/6. So either way here, you get 1/2. Any questions? All right. So kind of the last basic idea we need is the concept of independence. Often independence and mutual exclusivity can be confused for one another. Mutual exclusivity, remember, it means that there's no elements in the intersection of 2 events. And that's something that we can kind of know about. Independence is rarely something we can intuit. And I hope that I have an example here for you that explains that. But there is a mathematical test for independence. So if we have 2 events and we know what the probability of their intersection is and the marginal probabilities of each of it happening, if we can take that product and it's equivalent to this intersection, we know that it's independent. And all of this is coming from that definition of conditional probability that we just learned. So if we focus on this line here in the middle, this is just what we learned, the formula for conditional probability of A given B, right? And then totally lost my train of thought. Oh, right. If using this assumption, using the fact that we know that if we condition on B or another definition of independence, then the probability of A given B is just the same thing as the probability of A. So independence means that if we know that B happened, it doesn't give us any extra information about A. So to get from here to here, we're replacing P of A given B with P of A. And then we can rearrange this a little bit to get this test for independence. So quite often, if you're ever like in a probability class, you are always asked to test for independence. It is like rarely something that, like I said, that you can intuit or know. This is one of the few examples that I'm going to show where you can really think about this intuitively. So here we have event A, which is rolling numbers 1, 2, 3, or 4. Event B in red is the odd numbers. The intersection of those events is just the purple squares, 1 and 3. So here we know the probability of event A is 4/6, event B it's 3/6, and their intersection is 2/6. And we can check here that their product, in fact, the 4/6 times the 3/6 is equal to 2/6. So that's the formal mathematical test. The intuition here is, if I just ask you first off, what's the probability of event A getting a 1, 2, 3, or 4, right? You're going to divide the 4 squares here, the size of that event, by 6, right? Now, if I tell you it's an odd number, our restricted sample space becomes 1, 3, and 5 here, right? And now if I want to know if I get a number that is less than 4 out of that restricted sample space, it's going to be this 2 over, this doesn't make sense. Oh, that's because we're calculating B given A. Let me reverse this example. I'm really sorry. If the given event is that it's 1, 2, 3, or 4, and the original event is B, so instead of A given B, we think about the event of B given A. The probability of that happening from the full sample space is just this 3 over 6, right? The 1, 3, and 5 over the whole sample space of 6. If I then go and tell you, hey, I rolled the die and it's 4 or less, that restricts our sample space to these 4 blue squares, of which half are still odd, right? So knowing that event A happened, now the probability of event B happening is 2 over 4, which is also 1/2. We haven't changed or learned anything new about the chance of the event B happening. So these would be independent events. Okay. If we think about another example, right, you could restrict the sample space in a way where your probability does change. So this definition of conditional probability and these notions of independence are actually how we can learn about Bayes' rule. So here we just looked at the first equation on the first line here before the arrow when we defined conditional probability, right? The probability of A given B is their intersection divided by the probability of event B. We can make the same statement about probability B given A, which is the probability of the intersection of those two events divided by the probability of event A. And if we rearrange both of these equations, right, here we multiply both sides by P of B, here we multiply both sides by P of A. Then you can see the right-hand side of both of these equations is now the probability of the intersection of A and B, right? So here I know that P of A given B times P of B should give me this value, and also P of B given A times P of A will give me that same value. Well, if they're both equal to P of A intersect B, we can then say they must be equal to one another, right? So that's how we get to this line right here. And then if we rearrange one step further by dividing both sides by P of B, we get the formation of Bayes' rule, which you may have learned before. This idea that you can find out a conditional probability as a function of the reverse conditional probability, right? So you can learn something about the probability of A given B from the probability of B given A. Any questions before we go into kind of the canonical Bayes rule practice example? This is kind of the end of our review of probability. All right. So you've all, maybe not all of you, but many of you have probably encountered this example before. It's kind of the classic way to teach Bayes' rule in a classroom or in a textbook. But you have some disease that has a prevalence in the population. For our example, that prevalence is going to be 1%. And then you have a blood test for this disease that is highly sensitive and specific. And so sensitivity meaning that the probability of getting a positive test, given that you are actually sick. Specificity is the probability of getting a negative test, given that you are actually not sick. So we know for the specificity, it's 98% if someone has the disease, there's a 98% chance they'll test positive. If someone doesn't have the disease, there's a 95% chance they will test negative. That's all well and good. These are things we learn through trials, right? And through observation of applying these tests to lots and lots of people. But if I go into the doctor and I get a positive on this blood test, the question I'm actually interested in as a patient is, what's the probability I'm actually sick given I tested positive, right? The opposite information we know from sensitivity, right? So we're going to use all of this information to figure out that question. So what we know so far and kind of converting it into probability notation is that the probability that someone's test is positive given they have a disease is 0.98. Now, if you are sick in this little made-up world that we've created, there are only two ways or two possible outcomes in the sample space of taking the test. You can either test positive or negative, right? And so since the probability of either of those outcomes happening is 1, we also learn from the specificity that the probability of testing negative, given that I am sick, is actually just 0.02, right? Similarly, from the sensitivity, or excuse me, the specificity, we learned the probability of testing negative, given you aren't sick, is 95 or 0.95, and the probability of a false positive is 0.05. Finally, we know that in the population writ large, the prevalence is 1%, and therefore the proportion of the population without the disease, or the probability of getting a not sick person if you select a person from the population at random, is 0.99. Okay. So we can use all of this information and our little formula we learned for Bayes' rule, which is over here on the left, right? This is what happened to me. I went to the doctor, I got a positive test. Now I want to know what's the chance that I'm actually sick. I can calculate that as a function of some other things we already know, including the sensitivity of the test, and the prevalence of the disease in the population, and then the probability here in the denominator of testing positive, just fully nonstop testing positive. We don't have that in our handy little bullets up here. We don't have that calculated, but again, think about this contrived simplistic world we have. There are two ways to test positive in our universal set. You can test positive and not be sick. You can test positive and be sick, right? And there should be no shared space between those two events, right? The intersection of those two events should be empty. I can't be both sick and not sick at the same time. So we can replace our numerator with the sum of the probability of testing positive while being sick and the probability of testing positive while not being sick. Again, these do not show up in our handy 6 pieces of information. But if we remember the definition of conditional probability, we can replace any intersection, right, with a conditional probability times the probability of the event that's been conditioned on. So that's what we're doing here. Instead of doing the probability of testing positive and being sick, I want to multiply the probability of testing positive given I am sick times the probability of being sick, and same thing for not being sick. And we can just replace those there. And now this probability is a function of only pieces of information that I do in fact know, right? So the numerator there would be 0.98, the sensitivity times the disease prevalence. The denominator is that same term plus the probability of testing positive and not being sick, or testing positive given that you're not sick times the probability of not being sick. So in this toy example, after all that, if I've gotten a positive test back, I've calculated that the probability that I'm actually sick is only 16.5%, right? And that is actually a function here of the low prevalence in the population. If we change that number, this number would get quite high. And of course, it is a function of sensitivity and specificity. As close as those are to 1, this would be higher. Any questions about this simple example before we kind of dive into the real part of the lecture? Anyone online? All right, so let's talk about likelihoods. To talk about likelihoods, we need to think about random variables first. So we've kind of talked about probability, and then the step from probability to statistics often involves this introduction of the concept of random variables. So A random variable is actually a concept in math that assigns a number to each element in a sample space when we're thinking about an experiment in the probability sense. You can also think about it, kind of intuitively as an answer to a question you're going to ask about each element in the space. It's a variable because the answer will be different for each element in the sample space. And it's random because of this idea of experimentation and observation. We can't predict the outcome until we have observed the experiment itself. So examples of random variables in the context of really simple experiments that we've talked about, if our experiment is to roll a die and our sample space is the numbers 1 through 6, one very simple random variable might just be the number rolled, right? Where X takes on the value of the face that you roll. So if I were to roll a die 100 times, I might have X1 through X100 and they all have values 1 through 6. If I roll 2 die and I have this sample space where each pair are what comes up on the 2 faces that I roll, maybe a interesting random variable here is the sum of the 2 dice. So that has possible values 2 through 12 and multiple, the pair 1 and 2 along with the pair 2 and 3 are both going to yield the value 3 of the random variable, right? So 2 different events in the sample space are going to map onto one value of the random variable. So if we have a discrete random variable like this, where we have a finite number of outcomes that we can count, we can look at the probability distribution of this random variable by simply enumerating the probabilities that X takes on any value that it possibly can. So in the case of rolling a fair die, we could simply describe what we call the probability distribution, or we might call the probability mass function if we want to get really specific, is this table right here. X can take on the values 1 through 6, and the probability that X equals each of those numbers 1, 2, 3, 4, 5, 6 is just 1/6, right? The probability distribution function is going to be defined differently in statistics for continuous and discrete random variables. So as I just said before, this phrase probability mass function, or a PMF, is what we call the probability distribution function of a discrete random variable. So a discrete random variable can have either finite or infinite possible outcomes. But they have to be countable, which is kind of a weird mathematical concept. But for example, if we want to flip a coin until we get a heads, right? That is a process where, particularly depending on the weighting of the coin, you could hypothetically flip the coin an infinite number of times until you get a heads, right? But if you're counting, you should always be able to record the like the index or the flip number at which that occurs. But hypothetically, you could go on and on and on and do that forever. So that would be countable and infinite. But usually we're talking about something with just a finite number of outcomes here. And so I can either write that table that we had before, right? Or I can display the PMF in a bar graph where the height of the bars are the probability that X takes on, or the random variable takes on, the values in the x-axis. Okay. For continuous random variables like random normal variables or exponential variables, the probability density function is a curve. It is not this kind of step function or discrete, bar plot, however you want to think about that. The probability density function is going to be a continuous curve. It usually goes on from negative infinity to positive infinity, that there are some continuous random variables that are only positive, in which case the support of these would be 0 to infinity. And then also there's uniform random variables where we might have a uniform distribution between 2 numbers. So they wouldn't go on from infinity to negative infinity, but if we had, say, a uniform distribution on the interval 0 to 1, there's still an infinite number of values between 0 and 1 that this random variable could take on. So when we have these PDFs, like the bell curve or the normal distribution that you see here, this is the PDF for the normal distribution. there are too many values that X could take on. And so if we want to calculate the probability that X equals C, it's actually mathematically always equivalent to 0. So notice that for the discrete random variables in the PMF, the form of this is the probability that X equals some value. That is always 0 for any value. And so if we look at this figure on the right, this center line is meant to indicate how these kind of continuous things work. When we have a continuous curve like this, we can calculate the area underneath the curve, like this area in blue between 2 points A and B. Because the area under the total curve always is 1, it means that the area of rectangles like these, or whatever shape we really want to call that, I guess it's kind of a trapezoid, are always can always be interpreted as the probability that X lies between those two variables. So here, the probability that A is less than X is less than B is going to be the area of that blue square, and that's going to be positive, right? We have a width of B minus A, and then we have some height that changes over that. But when we look now back at the idea of trying to draw the probability that X equals C on this function, there's no width, right? We don't have this B minus A. We have a line. We don't have a rectangle or a shape. There is nothing to take the area of. The area of a line is 0. So if we want to describe the kind of behavior of a random variable, we want to think about it as a discrete or continuous, and then go on and think about a PMF or a PDF. So you have probably heard the phrase likelihood. Hopefully you've heard these phrases PMF and PDF. But I'm introducing this concept of probability density functions mainly to drive home the point about what is the difference between a distributional function or a mass function and a likelihood. So first, let's think about the binomial random variable, where we're flipping a coin n times, and we have a probability of getting a heads of P in each flip, which is independent of each other flip. We can write out the probability mass function. So for a lot of our canonical random variables that are discrete, we don't make tables like this. We actually have equations that describe the values we would calculate if we were to make this table. So this is that function, the probability mass function for a binomial random variable. And note, it is the probability that X equals little x conditional on or given the parameters of this distribution N and P, which are the number of trials and the probability of success. So in this case, if I tell you what N is, how many flips of a coin we're going to do, and what the probability of getting a heads, you could use this equation, and then I ask you the question, if N is 100, and P is 0.25, I could ask you what's the probability that X equals 25, and you could go calculate that, right? You just plug and chug. But what you already knew, what is given here and behind the vertical line in the probability statement, right, is N and P. Those things are known. Now, when you have binomial data, what you end up knowing is that you flipped a coin 100 times and you got 57 heads, but you don't actually know P, right? That's like the whole purpose of this experiment of flipping coins, is to determine the probability of getting a head. So we talk all the time in stats classes about these important canonical probability distributions, but when we are actually starting to do statistics with data in our hand, we are not in the probability framework. We're in a statistical framework where we actually have the X's, and we're trying to learn something about the parameters. We don't have the parameters so that we can, simulate data. We've observed data and we don't know these parameters. So in this case, where say I flipped a coin 100 times and I got 57 heads, and I'm trying to estimate the probability of seeing a heads, I will define a likelihood, not a probability mass function. The right-hand side of this equation is the exact same as the right-hand side of the probability mass function. But what is given or known here is now X and N. and not P. So a likelihood is a function of a parameter of a statistical distribution, whereas a probability mass function or a probability density function is a function of a random variable, okay, that has a distribution. Is that clear? Yeah, so a probability mass function or a probability density function is going to be a function of a random variable. And when I say function of random variable, I mean that you could have actual numeric values for n and p to plug into this equation, and the only remaining variable left over would be the little x's, right? But once we've done an experiment and observed data, when we come to statistics with our data, we're in a different paradigm. We don't know our parameter of interest P, and we've observed the outcome of a random variable X. And then of course we know N in the binomial case. So the likelihood is a function of a parameter, and the probability density function is a function of a random variable. That helpful? Anyone online have questions about this? Okay.
Sorry, I have a question.
Yeah.
I guess I'm guessing the math just works out, but it seems wild to me that the likelihood and the two equations look exactly the same.
That's by design. So they are the same equations. The only difference is how the inside of these parentheses are set up. Here we have X given N and P, and here we have P given X and N. So it's really about what we come to the table knowing. For instance, if I go tell you, I have a fair coin, meaning P is 0.5, and I say you're going to flip the coin 100 times, you would put in 100 everywhere we have an N, you'd put a 0.5 everywhere we have a P. And then if I asked you the question, what's the probability that X equals 50, that we get 50 heads, you would continue to fill in 50 everywhere there's an X, and then we have something we can calculate, right? But once you've done your data collection, so maybe it's not flipping a coin, maybe it's carrying out a survey and asking someone about their disease status for some disease, right? What you have now is the number of people with the disease in your data and the number of people you asked. And that can be plugged in everywhere in this formula as it is here. But what is unknown, the remaining unknown now, is just P. It's not X. So they're exactly the same, and that's by design. The difference is what is known in each case. And we use this likelihood in maximum likelihood estimation to then estimate P from our data, right? Okay. Okay, and so here's the same thing with a normal distribution. Say we have in observations xi, and we know that each one of them, say, is normal with a mean mu and sigma squared. Then this is the probability distribution function for each of those xi's. But once we have the data and we've collected it to learn something about the population mu, right? What we actually only know here is xi and the number n. We have all of our x's and we have the n, and we're going to use that to learn something about mu or sigma squared. This becomes a likelihood. So now we put an L there instead of a P. And what's the function arguments, what's in front of the given sign, are mu and sigma squared, whereas in the probability distribution function, those are known. Okay. All right. Let's do a little time check. Okay, not bad. The rest of this is kind of the meat. Does anyone feel the need for like a quick bathroom break, or do we want to go? How's everyone feeling? Any thoughts online? Okay, thank you. I just needed one person. Okay, cool. Let's come back at 10:25 then, okay? right. Let's get back to it. Okay, so from here on out, this is really like, that was kind of all of the building blocks we needed to be able to talk about kind of the most basic sense of Bayesian models. So what does Bayes' rule, what we just learned to, have to do with Bayesian statistics? Well, Bayesian statistics is a very clever reframing or use rather of Bayes' rule. But beyond that, they don't really have much in common. So just using Bayes' rule does not make Bayesian statistics. But in Bayesian statistics, we are often trying to learn about parameters of some distribution that we're going to call theta here from data we observed, which we're going to call y. So to get information about the values theta, which is a random variable in this case, but is a parameter in other cases, and is a parameter of the model, based on our data y, we are going to use Bayes' rule and rewrite this as the probability of y given theta, some probability distribution on theta, and then dividing by the probability of y. So we call this right here the posterior in Bayesian statistics. That is the distribution of the parameters we wanted to learn about, conditional on the data we saw. Okay, that's kind of the whole goal of all statistics, not just Bayesian statistics, right? Even frequent statistics, we want to learn something about a parameter, whether it's a normal mean or what have you, a binomial probability, from the data that we've observed. We call this piece, the probability of y given the parameters, the likelihood, right? Which is confusing because it's written in this form, but what it really is a likelihood. That's what we call it. But what is observed in it are the y's, okay? So we now know, even though this is written as the probability of y given theta, what is actually plugged in and known here are the y's. So this is kind of an idiosyncrasy between the way I introduce these things in how we're talking about the function and what's before the given line. But if I were to have observed data, normal data, and instead of these x's, I have y's, then what I'm plugging in here is the observed data for all my y's. And what I don't know is, say, the mu or the sigma square or both of those for a normal distribution. The prior is what we call this P of theta, and that's going to be the assumed distribution that the distribution that we assume for these parameters in absence of any data. Here on the bottom, the probability of the data without conditioning on theta or over all thetas is what we call the normalizing constant. So when you hear the phrase a Bayesian posterior or priors, what we're talking about is really this numerator, the product of the likelihood and the prior, and then what comes out on the other end. And we're not going to spend much time talking about the normalizing constant for now. Okay. So in this, in our simple example, there's not really a one-to-one correlation between observing this like binomial of one and a full Bayesian model, but we can kind of break it down like this, right? We knew that we saw a positive test, or that our random variable, which assigned a value of 1 if the test was positive and gets assigned a value of 0 when the test is negative, took on the value of 1. And what I want to know is whether I have the disease, or what is the chance that I have the disease, right? So that is the P of theta now given my y. I know from the sensitivity, the probability of getting that positive test given my sickness, and I have a prior information about the probability of the disease. And then this whole thing on the bottom is the P of X. What's the probability of getting a 1 when I average over all possible values of my parameter? So when I'm positive and when I'm negative is basically what's happening here. Okay. So in general, that P of theta is a probability distribution over possible values. Oh, sorry, of the posterior. Sorry, thank you, 16. The posterior is the probability distribution of the parameter given the data we saw, and of course conditional on the prior that we selected. Okay, but here the likelihood is gonna have where we actually have observed Y, right? And so if we can calculate all of these things, what we can learn is what are the possible values of theta based on our data. So P theta, like I said, is the probability distribution of possible values of theta, or the prior is. Often there's kind of a line about Bayesian statistics where it's like, it's so great, you can incorporate prior scientific knowledge into your models. And this would be where you do it. You would specify some sort of prior on your parameter that mimics what you know. For example, if you know that your parameter can only be positive, right? That would be something you would want to bake in. Maybe you know it has a hard maximum, that's something you can bake in. Or maybe you know some distribution of previously observed values. But in absence of those kind of things, what is most common actually is to put an uninformative prior on theta. So something like if we're thinking about a normal mean or regression coefficients in linear regression, we're going to put a normal prior with a mean of 0 and a very, very large variance on it, so that almost any value is hypothetically plausible under the prior. But if we have enough data, we're going to learn about the specific place in that distribution that the parameter falls. So the hard part of Bayesian statistics is this denominator, the normalizing constant or the marginal distribution of the data. Sometimes you'll see this called the prior predictive distribution as well. So like I said before, it's the probability of seeing Y, but we've sort of averaged over all the possible values of theta. And that was easy to see here, right? What was the probability of getting a 1 but we've done a weighted average here, weighted on the probability of being sick or not. And those are the two values of my parameters. So in a discrete setting, we do this by summing over these terms for all possible values of theta. That's what we just did when we did our Bayes rule example, right? There were 2 ways to test positive. For continuous variables, this is the same thing. It's just an integral, right? Integrals, if you aren't super familiar with them, they're really just fancy infinite sums. So there's just a direct kind of connection between what we did with Bayes' rule to the more continuous case. So there's this cool concept of conjugacy, and until computers got really good, and I mean like in the past 30 years, really good, Bayesian statistics has existed essentially since the 1700s, but it could not be done in the ways in which we think about it now, because there was not enough computing power. But there are pairs of likelihood and prior distribution families that lead us to a posterior that is analytically tractable, or something that we can actually write down and know. Okay, so for the binomial likelihood, the conjugate prior family is the beta. For the multinomial, it's something called the Dirichlet. For Poisson, it's a gamma prior on the rate. For an exponential, it's also a gamma prior on the rate. For the normal, it's the normal itself. If I want to know a normal mean, and I know sigma squared is known, kind of that first example you learn in your intro to stat class, then the prior on my mean should be normal, and then I get a normal posterior. If we want to estimate the variance itself, we would put a normal prior on the mean and what's called an inverse gamma. which is basically just a gamma distribution on 1 over the value of the variance, and we'll get out a nice prior. So this is a nice table just to know. What this looks like in practice, we'll kind of walk through, and we're going to start with the beta binomial model because it's a little bit easier to actually write down all of the numbers that we'd be plugging in and kind of figure this out. If you're interested, the figures that are going to be in this next little set come from a pretty cool package called Bayes rules. And there's really easy functions that allow you to make these nice prior likelihood posterior plots based on conjugate families. So that's just kind of neat if you didn't know about it. So imagine we, instead of the one person, me, who took the test in our Bayes rule example, we test 100 individuals for the disease, and we still have that same prevalence of 1%, and 5 of them test positive. So our likelihood then is going to be this binomial likelihood where we plugged in the values for n and x, right? X was 5, n is 100, n minus x is 95. And the only thing not filled in here is p, right? That's what we want to learn about, is the actual, the probability or the true prevalence that what we're going to estimate is the prevalence from the population. So this is a little bit of a different example than what we did in the first one. But here, our parameter of interest that we're trying to estimate is p. That's the theta that we've been talking about here, right? So we just looked at this. It is a function of theta. Everything else has been plugged in. We need to come up with a prior for that p, for our parameter, and then we can learn something about p based on our data. So following conjugacy, we're going to use the beta family to probability family to construct a prior. And we're going to, oh my gosh. Sorry, this should be a beta right here. The beta prior contains what are called gamma functions, but this is not a gamma prior. So this should be a beta. I'm really sorry. The beta distribution has 2 parameters, alpha and beta, and we're just going to set them to be 2 and 2 for now. And so if I were to write out the prior with these alpha and beta set at 2 for p, this is what it looks like. Okay, so you can see that there's some kind of similar bones here, right? They both have the bones of a Bernoulli distribution or a binomial distribution where we have p to some power and 1 minus p to some power. So with some clever algebra, you can kind of rearrange this and learn what p of y is, and then you get out that p conditional on what we observed when we did 100 tests and observed 5 positives is also a beta distribution with the new parameters being 5 plus 2 and 2 plus 100 minus 5, okay, right? This is x or y in our binomial and n minus y here. Math aside, looking at the picture is kind of the nicer thing. In yellow, we have the prior on p. And so the x-axis here, it says pi, but this is really referring to the p, the parameter that we're trying to estimate here, okay? So you can see that this gamma or this beta 2 prior, it covers almost the whole space between 0 and 1 with more weight given to the values in the middle, but still this doesn't really exclude any values except for 1 and 0 themselves, right? So we would call this a relatively uninformative prior across the whole possible range of possible values of p in a binomial distribution. In blue, we have the likelihood, which is what we observed from our data. Okay, so that's over here. That is this distribution. And what we see in the posterior, and the whole point of going through these plots, is to show that the posterior is a product. I mean, we saw this in the formula. It is a product of the likelihood in the prior with some scaling on the bottom. But visually, it's also that. So we started with this pretty uninformative prior, but we tested 100 individuals And so we have pretty decent information. And so you can see that the posterior really mimics our likelihood. And that is sort of the goal and the underlying asymptotics of Bayesian statistics, and why it works is that as your sample size grows, or as you have more information, your posterior is going to mimic your likelihood and not your prior. To reply to Fan, the goal of Bayesian analysis is to give us a full distributional estimate of a parameter. So one thing in frequent statistics, what we get out is a point estimate, like X bar, right, for mu, and we get a standard error on that estimate. And we can construct that confidence interval that's symmetric and has kind of a weird interpretation, but we're all pretty used to that. What Bayesian statistics buys you, and sort of why would you do this instead of just the frequentist thing, is that we don't just get a point estimate and a standard error, we actually get a distribution. So if that posterior distribution is actually not symmetric, the kind of traditional frequentist confidence intervals won't show you that. So you get to see the whole distribution. The other thing that's really cool is you get to you can sample from that distribution. It is a distribution for a random variable. So you can simulate data under that distribution, and for any parameters in your model or any function of those parameters, you can get a probability distribution of that transformation of the variable, which in frequentist statistics is a bit harder. You can do it with the delta method, but it only works with certain types of transformations. So, and then you said the goal of trying to specify the correct prior. I would say that's not the goal. It's just that until computers got better, these were the only known pairs of priors and likelihoods that produced a posterior that also fell into the classes of these named probability distributions that we all know, like a binomial, like a gamma. So this kind of Bayesian setup is always true. The problem is in much harder examples, and kind of the most common examples where you have to end up using MCMC, is that that posterior is not a normal or a gamma or something we know the name for, which makes it harder to sample from. So we're just kind of focusing on this kind of ancient branch, if you will, of Bayesian statistics to kind of get the nomenclature and the math down. Now for Andy, yes. So usually in a prior, you would pick the values of the parameters of the prior, right? Our goal here is to estimate P. And we can see that this alpha and beta I've chosen give a pretty diffuse prior across the values of 0 to 1. We can try it with other values. If you wanted to, for some reason, also learn about alpha and beta, your Bayesian model would simply just become more complicated, in that we would then need to place, we wouldn't specify alpha as 2 and beta as 2, but we would then need to place a prior on alpha, or what we call a hyperprior, on alpha and beta. So, there are some people in the Bayesian camp that kind of think if you're not doing full Bayes, which basically means that you're always putting a prior on the parameters of your priors, you're not really doing Bayesian. But I think it really should be a modeling decision around how much data you have and whether estimating that parameter is helpful for you or not, right? Are you going to use it in any analysis? If not, you might as well just specify a wide prior and maybe do some sensitivity analyses and make sure other priors don't give you different results. Is that helpful, Fan and Andy?
And this is Andy, just real quick. I guess the answer is insensitive to the initial assumption of alpha and beta in this case.
Well, that's the goal. We'll see in a few examples that is really dependent upon your sample size and how much information is in your data. Your prior will be much more informative and impactful on your posterior if you have less information in your likelihood. So here I've changed the prior to to alpha equals 5 and beta equals 1. And here we see that that prior, I would say, is no longer uninformative, right? Here we're saying, it could basically be any value between 0 and 1 with, why not 0.5 if we don't know better, is kind of what this prior is saying. Whereas this one is saying, I think it's probably between 0.5 and 1, right? Still, we have enough data to the contrary that our posterior is still down in this bottom part of the distribution, but you can see that the posterior is now, you can fully see that it is between the likelihood and the prior. That is always the case. It's hard to see now because this prior of alpha equals 2, beta equals 2 did give some weight to where we actually observe our data to be, which means that the posterior is kind of right in line with the likelihood. Here, based on the prior provided, we would need more information to pull the posterior to the same position. Does that make sense to y'all? That's kind of, this is what I really want you to get out of this set of slides, is this intuition of how visually the prior, the posterior, and the likelihood are working together. Here is an even more diverse or extreme example, where instead of testing 100 people and getting 5 positives, we've only tested 10 people and got 1 positive, and I still have that beta 5-1 prior that is saying, like, largely, certainly it's above 25% and most likely above 0.5%. Now you see that with a smaller sample size, first of all, the distribution of my likelihood is much wider than it is here, reflecting that. And now the posterior is much more in between the prior and the likelihood, right? It is leaning much more heavily on the prior because there is not as much information in the likelihood when we only have 10 data points. Is that clear to everyone? All right. So mathematically, we can write this down. If we have, X, we have n Bernoullis, and they're all, or binary variables, Bernoullis, they all have probability P, so that the sum of those is binomial NP, and we put a beta, alpha, beta prior on P. If we wanted to work out and get this posterior, I already told you that the posterior is a beta. This is how we would start. This is always kind of the first step in any Bayesian modeling, is writing down your model. So I know I want to learn about P from Y and N. Well, that's going to be a product of my likelihood times my prior divided by this normalizing constant. The second step you always take is to drop any terms unrelated to your parameter of interest, including the denominator. And so instead of equals to, we'll use this proportional to sign when we do the math. So we drop that, and now we know how to write this down. Here's my likelihood, here is my prior. And again, I get to drop the terms without P, right? So I get to drop this whole complicated thing. I get to drop all of this in front. And I'm just left with these 2 terms that look like a Bernoulli, right? P to some power 1 minus P to some power. And with a lot more algebra, what you find out is that that P given Y and N is going to be another beta whose parameters are now alpha plus Y and beta plus N minus Y. And from that, because it is a named distribution and we know how to calculate means and variances from that, we would take as our estimate of P from this data, alpha plus the number of positives we saw divided by alpha plus beta plus the number of trials, right? And the variance for that estimate would be plugging in all of those values here, okay? So that would be at the end of this, if I wanted to, in these examples, if I wanted to pick an estimate here for this one, I would use the values 5 and 1 of alpha and beta and y equals 1 and n equals 10 and plug in everywhere here. And now I would have an estimate of the probability of the disease and the variance around that parameter. Okay. Any questions before we dive into the normal? Okay, so we're going to do a similar exercise with the normal distribution. And this is kind of a very silly example, but suppose I'm, teaching an undergrad course and I ask a friend, what is the prior you would put on the age distribution of my class? So if they say that it's normal, 18 variance of 1, and I ask 10 or 100 students in my class their age, and I get, these answers. We can see the prior here in yellow is centered around 18, right? That's just and then now the posterior and the likelihood, even in the 10 case, but especially in the 100 case, are almost indistinguishable, right? And that's largely because in this case, the prior is pretty well centered on the data, right? So we actually didn't need a lot of evidence in this case to get a posterior with a smaller variance, because the prior was actually in line with our data. Of course, this is not something we can ever rely on or expect in our analyses, but this is kind of the motivator for, if you do have prior scientific information, how you might want to work that into your data. So I asked someone else and they say that their prior is 20 with a standard deviation of 1. And here we start to see a little bit of difference, right? No longer are they kind of all in line. There is some difference in the posterior and prior, but again, 18 is well within this prior distribution's like main support, right? So we get similar estimates in each of these cases, but what's going to vary here are the standard errors, or I guess they're not standard errors in Bayesian, but the width of these distributions are going to vary based on how far the prior is away from the data. So when we're doing like linear regression and Bayesian statistics, or if you were to just fit with like the most uninformative prior, we're probably going to do a mean zero prior with a really large variance. I put 10 here, but for instance, like an n-law, if you're going to fit a linear regression model, the prior I think is normal 0, 100,000. Okay, so very big variance. You can see here, this is much more diffuse. It goes from -40, negative infinity, positive infinity. Even if I only have 10 students, we can see that the prior and the posterior are pulled pretty far away. And the posterior is really reflecting the likelihood. And the only thing that really changes a little bit when we have 100 more students to ask is we're getting, a tighter and tighter posterior. Now, if the prior we put on here was mu equals 0, sigma squared equals 1, we can see the standard normal prior off to the left. And with 10 observations, we see our likelihood here, and that our posterior has been pulled down a little bit by the prior, right? But it's still pretty precisely estimated, just kind of, off. But if we up our sample size, again, here, we're in this situation where it clearly doesn't matter what prior we put on here. We have enough information to get basically the same posterior every time. Any questions about those examples? We're about to do a lot of algebra, so, forgive me later. Okay, so just like with the beta binomial model, for this normal model, we have some random variable y with mean mu, and we know sigma squared. This is like intro to stat 101. Assume you know something that you never know in real life. But under that assumption, if we put a prior on the normal mean that says it's normal theta with a different variance of tau squared, where we know what those values are, what is the distribution now of mu given our data y, our one value y, our sigma squared that we know, and then the prior mean and variance. This is also AKA the posterior distribution of mu, right? We've conditioned now on everything else. It's actually normal, that's the conjugacy. And it's kind of cool. You can see here that the mean now is going to be a weighted prior between our observed data y and the prior value theta, where the weight is determined by the relative size of their two variances. Okay. And then the variance now is a combination of the prior variance and the observed variance. So we would get an estimator of mu here by using that formula for the mean, right? And then we would get a variance by just plugging that in. And those would be values we know in this case. We already know tau squared and sigma squared under the rules. So if you ever really want to do Bayesian statistics on your own, and you're going to do something more than just a quick linear regression or something that could be done in a package, you're going to need to know how to write down your models and find these posteriors. Like I said, they don't always have nice forms, but it's really helpful, I think, to have done some of these kind of canonical exercises. So we're going to go through the derivation of this posterior distribution. And then we're going to talk about a few more quick ones that you'll just have to take my word for me. Word for it. Okay, so we're going to do all of the math. I tried to make it so that it's easy to follow along with, but please let me know if you have questions here. So following what we did here, where I said you get to kind of start by dropping the denominator, right? And you do proportional to. And then we want to plug in the actual equations for the likelihood and prior. Then we can drop terms that don't contain the parameter of interest in them and go on from there. So that's where we're starting here. We've dropped the denominator, and our likelihood in this case is y given mu and sigma squared, right? Our prior is this distribution on mu given theta and tau squared. And then we drop the denominator. And if we plug in the normal priors and likelihood here, this is what they look like, right? We got y minus mu squared, and we know y and have observed it. And then in the prior, we have mu minus theta squared, where theta is some value that we know we put on the prior mean, and mu is the thing we're trying to learn about in these equations, right? So that means I can drop everything in this expression that doesn't contain mu. So I get rid of the kind of the constants in the front of the normal, and I'm just left with the two kernels here, right? So the first thing we're going to do is expand the squared terms in each of these numerators, right? So FOIL it out, we get y squared minus 2y mu plus mu squared. And in the second one, we get mu squared minus 2 mu theta plus theta squared. And just for room's sake, I kind of alternate between multiplying two exponents together and then combining them in the same exponent. And just remember that when you multiply e to the something times e to the something, you get to add them inside. So I'll kind of go back and forth between that. And so again, here we get to drop the terms that don't contain mu, which would be this theta squared term and this y squared term, right? I can get rid of those. So the first thing we're going to do inside this exponent, we have two fractions, and recall what you used to do when you wanted to add or subtract two fractions. We have to find the least common denominator and make that the new denominator, right? And then once they have the same denominator, we can just add and subtract in the numerator. So the least common denominator between 2 sigma squared and 2 tau squared is going to be 2 sigma squared tau squared. Like that's a pretty easy one to see, right? So I'm going to multiply each of these terms by what I call fancy 1. That's basically all any algebra is multiplying by fancy 1 or adding fancy 0. So I'm going to multiply this left-hand side by tau squared over tau squared, and on the right-hand side by sigma squared over sigma squared. And then I'm just going to combine like terms with this denominator, right? So if I multiply by tau squared up here, now I have minus 2y tau squared times mu, and minus from over here 2 theta sigma squared times mu, right? And then for the squared terms, I have, I have tau squared times mu squared and sigma squared times mu squared, right? So if we combine like terms in our parameter of interest, mu, means I'm going to bring together the two things that are multiplied by mu here, so that I have minus 2 y tau squared minus 2 theta sigma squared times mu. And in red here, I have sigma squared plus tau squared times mu. Right? All good? So if I call these B and A, these coefficients on mu squared and mu, I hope something kind of deep, dark in your brain is like, oh, I remember this. This reminds me of the quadratic formula. We're not going to talk about the quadratic formula, but we are going to do what's called completing the square, if you remember this. We have something that looks like a quadratic formula, and we'd like to get it into a nice thing that's like mu plus something parentheses squared, which will start to look like a normal, right? So if you don't remember what completing the square is, this is kind of the aside on that. If we have up the top some coefficient on x and a coefficient on x squared, we can turn that into a term that looks like x plus some constant squared, completing the square with the following steps. First, you want to make sure that coefficient on x squared is equal to 1. So I'm going to divide through by a, so that my coefficient on x is just b over a. And then you take half of that coefficient and you square it and you add and subtract it. So this is a case of adding fancy zero, right? I'm adding this constant squared and I'm subtracting this constant squared. And what it's going to allow me to do then is combine these three terms into x plus this constant squared. And then I have this just numbers left over, right? Nothing that contains x. So I can restart with something like this, where I have a coefficient in front of b, in front of x and x squared, and end up with something that is x plus a constant squared, and then something else that is a constant. Okay. Any questions before we go do this for real? So, this is where we were before, right? We have these two terms in front of our mu and our mu squared. We're going to call them b and a. Now, getting toward completing the square, the first thing I'm going to do is divide through by a. And this can also be thought of as actually multiplying by fancy 1. I have to divide the numerator and the denominator by a. So you could also think about this as multiplying the numerator times 1 over a and the denominator by 1 over a as well. So I get rid of the a in front of the mu squared. I have this coefficient b over a in front of mu, and now my denominator also has an a term in it. Following exactly, the kind of algorithm to complete the square, we're going to add half of that coefficient squared and subtract it. And here I'm kind of plugging the terms back in. So we have b over a, and here is the subtracted out part. So I have here now mu squared plus mu times something plus half of that something squared, which is exactly how I'm going to get my constant. So this is the piece that I'm going to turn into mu plus something squared, and nothing here now contains mu, which means I get to drop it like we have so many other times already. So here up in the numerator, right, I'm converting this first row into mu plus that term squared, or half that term squared, right? That's the completed square. And then I have this constant over here, not a function of mu. We're going to get to drop it in a second. I guess what I decided to do first here is deal with all these negatives. And remember that when we have a normal distribution, right, it's the variable minus the mean squared, right? So that's what I'm trying to do here in this step, is clean this up one step further, so that I can have these minus signs dealt with. And so here I divide the 2, right? I can get rid of the 2 here and here and cancel it in this part. And I can bring those negative signs to turn this into a minus sign and these two into positive signs. So now it looks like we have a normal kernel, except for this constant on the side, We dropped those terms. They're not related to mu. And now I have a kernel, and I can actually back out that P of Y, right? I just need to multiply and divide by a bunch of things here to get this to look like an actual normal distribution. But this is really all you have to take it, how far you have to take it algebra-wise, is, you know, because we're dealing with conjugate models, that we're expecting a normal. We want to do some algebraic massaging till we get this to look like mu minus something that would be its mean, and divided by something that would be its variance. So we kind of already looked at this before, but that would be the math behind how you show when you have a known sigma squared, a normal y, and a normal prior on mu, what the new mean and variance are for mu given your data. And again, it's this weighted average of the data and the prior mean weighted by their variances, and then, or the opposite variance actually. And then of course, this variance is now scaled a little bit and should be smaller than in the beginning. So this is just what we looked at, sorry. This is just what we looked at before. So that was kind of proving that. Any questions about that? The last two things I want to go over before we get out of here. I was sort of expecting someone to say, well, that's all well and good, but I never just have one data point. That is all of that algebra was saying we have one observation Y, and we've put a prior on mu. What do we learn about it? Usually we're in this situation, right? Where we have in Y's, IID, normal, mu. We, again, even if we simplify this and assume sigma squared is known, this is a bit more complicated. So what changes when you have more than one data point, sorry, I kind of screwed this up, that n should be up there, is the likelihood changes. The prior doesn't change. That's still a prior on the one variable mu, or one parameter mu. But under independence, we're allowed to multiply these individual priors for each yi, these normal priors together. So now the likelihood is the product of n yi's, where the exponent here is not just y, but it's yi minus mu squared, right? And because products of exponents can become exponents of sums, then we can move this into the numerator. And we have the prior. Again, we would start by dropping all the terms without mu. And I will spare you the algebra, but it would look a lot like what we just did. And here, now you see that the posterior estimate for this type of model would now be this weighted average of not y, but y bar, the average we saw in all of our data points, plus a weight on the prior mean. And you'll notice here, as n goes to infinity, this term that's multiplied by the prior mean is going to go to 0, right? So the more data we have, the closer to the posterior mean, excuse me, toward the observed mean, the posterior estimate is going to be. Okay, so I think that's this is kind of the more real deal. The first one was sort of an algebraic example, and then also just quickly, if we wanted to fit a regression model, this is again another sort of simplified example where you could probably work out the math yourself. But in this case, we're saying we have our y's, their IID normal, but the mean, instead of being mu, we're saying it's beta 0 plus beta 1 times some covariate xi, right? So now we need to put a prior on the vector beta on both beta 0 and beta 1. So that's what we're going to call theta. So here our vector beta, right, is a 2x1 vector with beta 0 and beta 1. And theta are going to be the prior means for each of those betas. And if we assume that the variance on these two covariance on those two parameters in the prior is known, and we assume the sigma squared is known, we can write out the likelihood again and actually end up putting it in matrix notation, which makes this algebra doable finally. So Here we have our y's, right? Our likelihood is still normal. The mean for our normal is x for each y is x transpose beta, right? That's the mean model. And then we have our known variance sigma squared. And then in our prior, we're going to use matrix notation, and we have the parameter we're trying to estimate, beta, minus its prior mean in a multivariate normal, all right? So again, you would start this algebra the exact same way if you wanted to calculate this by hand. You drop every term that doesn't have beta in it, so we can get rid of all of that stuff in the front of the normal. And then there is a version of completing the square for matrices if you would like to Google it yourself. But in the end, we get a very similar thing to what we saw, but now we're in the regression scenario. So we get, instead of x transpose x inverse x transpose y, which is the original regression estimator, right? We get something that looks like that, but instead of x transpose x inverse, we have the prior variance coming into play. And then in the numerator, again, we have this weighting between what we observed in our y's and the prior mean. And then the variance also looks very similar. So that is my last slide. Any questions? So, okay, the question in the room, for those of you who couldn't hear, is they felt like they missed something on what a conjugate model is and why we would need it. We don't need them now. In fact, almost no one, I mean, sometimes you still use conjugate models and there's a lot of good reasons, but if you're going to do something like linear regression, there are now packages where you can kind of just put stuff in. You don't even, I mean, you should be paying attention to the priors, but like it's taking care of everything for you. But long before that, the only way that you could estimate a posterior that we don't know what it looks like is to use Markov chain Monte Carlo. And that, the math for that has existed for a long time. The computing power to run those long enough to get estimates on anything but the simplest models has not existed until the past 3 decades. So people were using these known kind of analytical math relationships between these to put priors on things so that they could just write down the posterior estimate without needing a computer. You could still have done Bayesian statistics because you know exactly, oh, the posterior of this is going to be normal, and I just plug in these things and that's my estimate. But nowadays, what you really are doing is probably estimating some posterior that isn't a normal or a gamma or anything that we know that has a name to it. And so we're actually approximating that distribution in some way or sampling from it. And that can take a long time or requires a lot of computational approximation. So people still like, it is still very common, even in these like in law where, you know, you just can fit a regression model. The default priors for a lot of things are still an inverse gamma on variance, not because those are like the best priors for variances, but because they were used for so long because the math was easy. So there's a lot of legacies in Bayesian statistics today that come from this older use of conjugacy, even if now we're not limited to only these pairs of likelihoods and priors. Any other questions? Is it food? You can, I think, go ahead and start setting up. So next week, for those of you that'll see, what we're going to do is, again, we're not going to get all the way into kind of modern computation. We're going to take these ideas of conjugacy a little bit further, but actually do computing and do inference with data with these conjugate pairs. hopefully next year I will get to do my full series, and then we will build off of that and go into MCMC and then like STAN and stuff. But I think in my mind, these workshops are kind of for people who never get this background, and then even those of you who might be students at UW that like go to a CSSS class, like they're not going to cover this. They're going to start a few steps ahead of this. So. Yes, it will 16. So we'll actually calculate posteriors with real data and like talk like in a computational program and talk about actually doing inference, like what it would mean to have data fit these models and then talk about that in the same way we might all know how to talk about the results of a hypothesis test or a confidence interval. Yes, this is recorded, and we are trying to get them up. I don't know where we are with this, but we already put our seminars on the CSDE YouTube channel, and we are trying to upload these to there. I did update the the workshop page on our website to have the link to that GitHub, so you should be able to get the downloadable materials in perpetuity now. Okay. Any other questions or comments? All right. Thank y'all so much. Take care.